Welcome back to the continuation of our previous tutorial. Now we have seen what a set is. We said earlier a set is a combination of well-defined objects. Now let's look at the cardinality of a set. We made mention in our previous lecture that every set has what we called elements. Except the empty set. So the number of elements in a set is known as the cardinality of that particular set. In other words too, we say the size of the set. As well, other books say the order of the set. All these are acceptable. And it is denoted by, let's say for a set A, the order is denoted by A, like this. Or you could say n of A. In some books, you see car of A. So all these represent the cardinality of a set. The cardinality of a set depends on the set, the number of elements in a set. So let's say I have a set A equal to 2, 4, 6, 8, 10, 12. The cardinality of A is equal to, we just count the number of elements in a set. So 1, 2, 3, 4, 5, 6. And that is 6. Another example, let's say our set B contains X such that X is a vowel. The first thing we do is we define what a vowel is, or we have to know what a vowel is in order to solve this question. Now in the English alphabet we have 26 of them. Out of these 26, we have 5 as vowels and the remaining 21 being consonant. So basically, the order of B is equal to 5. Well, we may also list the elements of B and count them. So the vowel sounds are A, E, U, I, O. These are the vowel sounds. So when we count them, 1, 2, 3, 4, 5. And that's how come the order for B is 5. We can have more example. Let's say my set S is equal to X, such that X, the set of integers. Now we know the set of integers being positive and negative whole numbers, including 0. There are infinitely many members or elements in this set. So the order for S is infinite, meaning we cannot count it. Okay, so the order of this set is infinite. Other sets that have infinite size are, So we've made mention of the set of integers, the set of real numbers as well, the set of complex numbers, the set of natural numbers, the set of whole numbers. In fact, all the number systems are infinite or has infinite size. So you take note. What about if I have a set Jane to be 1, 2, 3, 4, and another set R to be 1, 2, 2, 3, 4, 4 like this. What is the order of Jane and what is the order of R? When we look at these two sets critically, we could see that they contain the same element, just that in R, some of the elements repeat themselves. And remember what we said a set is. We said a set is a collection of well-defined objects. And that means that the object needs to be unique. And so in set R, where the objects are repeating themselves, we can rewrite R to be 1, 2, 3, 4 by doing away with the repetitions. And this set and this set, we call them equal sets. Okay, so the order for Jane is, we count the number of elements there, 1, 2, 3, 4. So the order of 4, and this also has order of 4. Now this draw our attention to what we call equal sets. So let's quickly look at what equal sets are. We say two sets are equal if and only if they have same elements. In notation, set A and B, we say they are equal, written as A equal to B, if and only if for every x in A implies x is also in B. This is the only condition where we say two sets are equal. So regardless of how many times a particular item or element in a set is repeated, we don't care. All we care is the distinct element in the set. And so that's how come in this example we had 1, 2, 3, 4. Here we had 2 repeating itself and 4 repeating itself, but we squeezed it and we removed the duplicacy and maintained only unique elements in the set. So if you have a set like, say, S equal to X, Y, Z, and another set Y, say X, 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 Y, Z, X. These two sets, we say they are equal because they contain exactly the same elements. Regardless of the repetitions of the members in Y, we still see that they contain the same, or the elements are the same as that of S, just that some of them are repeating. So we say these two sets are equal. Note also that the arrangement of elements in a set does not matter. That is to say, if you have a set like, say, X, Y, Z, it is equal to Y, Z, X. and is still equal to z, x, y. Their positions does not matter. Next one. And another one we want us to look at is equivalent sets. Two sets A and B are said to be equivalent if and only if the order of A is equal to the order of B. If this condition holds, then we can conclude that the sets are equivalent. For example, if I have a set X containing A, B, C, D, and I have another set Y containing M, N, O, P. Because their orders are the same, the order for X is equal to 4 and the order for Y is also equal to 4. And because the order for X is equal to the order for Y, we say that X and Y are equivalent. We say X and Y are equivalent because their orders are the same. The next concept we are going to look at is subsets and supersets. In all the examples we have tried our hands on so far, we pick the sets from a larger set. So assuming I say the set of integers, and we know this is from negative infinity to positive infinity, which members we cannot list all. I can form, in fact, billions of subsets from the set of integers. And let me say my A is -2, -1, 1, 2, 3. I have formed a set from the set of integers and I'm calling it A. This is a subset of integers. I can also form another set B from A. When I take -2 and -1, I form a set. I can also form another set C, say -1, 1. This is also another set. I can form another one D, say -1, 2, 3. This is also another set. In fact, I can form up to certain number of subsets from A alone. Good. In this case, I say the sets B, C, and D are all subsets of A. And how do we represent that? In the case of B, we say that B is a subset of A. In the case of C, we say C is a subset of A. And that of D, we say D is a subset of A as well. Meanwhile, A itself is a subset of Z. In conclusion, all we are trying to establish here is that Z is a superset. Technical meaning to say that Z is the overall larger set from which we have formed all these sets. And we saw that the sets B, C, D are all subsets of A. Okay, so this is the concept of subsets and supersets. Let's take another example. Let's say we have a set S to be equal to A, B, C, D, E, from which we form another set B, say B, D, E, and also another set A, B, C, D, E. By observation, we see that the set B is a subset of S, and clearly set S is equal to set C. Instead of maybe writing this, we want to use the subset notation. So we say that C is a subset, but this time around we add a bar below the subset of S. And what this means is, in the first case, we say that B is a proper subset of S. However, in the case of C, we say this is improper subset. And improper subset because C contains every single element in S. And that is the fact we established that S equal to C, or the sets S and C are equal. So they are improper subsets of each other. So because they are equal, we can also write this as S is an improper subset of C. And this is only because they are equal sets. Otherwise, we cannot write it so. Literally, from our presentation so far, we have looked at comparability of sets. That is to say, we are comparing sets. So we've seen that given any two sets, A and B, A will either be a subset of B, or B will be a subset of A. Lastly, they may be equal. The same sense we say A. Good. So these are the ways of comparing two or more sets. So for example, if I have a set A containing the elements A, B, C, D, E, and the set B containing B, C, D, I can say that, or I can see clearly that every element in B is also in A. So I write this as B is a subset of A. If I add another set C to be equal to A, C, B, D, E, when I want to compare it to the set A, I say that C is equal to A, or C is an improper subset of A. All these two notations are the same. In the case where they are not equal, let's say what the notations you have written earlier is not equal, all we just do is that, for instance, if A is not a subset of B, we only cross this to mean that it is not a subset. In the second case, we say B is not a subset of A. And in the third case, we say A is not equal to B, or good. So this is the negation of the first statement or these statements. Practically, let's say we have a set A to be A, B, C, D, E, and a set B contain 1, 2, 3, and another set C to say C, D, E. You are being asked to compare these sets. So between A and B, we see that B is smaller than A in terms of size. So we say, since we cannot find any common element between the two of them, we say that B is not a subset of A. Neither is B a subset of C, or vice versa. However, we can see that C is a subset of A. So that is it.